Hello and welcome. Today, we're diving into one of the most powerful tools in machine learning, something that literally lets us predict the future using data from the past. We're talking about regression.
It's a question that's behind almost everything these days, from stock market forecasts to how much a new phone should cost. How can we look at everything that's already happened to make a really good, educated guess about what's just around the corner? Well, the answer, more often than not, lies in the set of powerful techniques we're going to break down today.
So, at its core, regression is all about teaching a computer by showing it a ton of examples. Think of it like this. We feed it a data set of inputs, and the outputs we already know go with them. The machine's job? To figure out the secret relationship between the two. The ultimate goal is for it to see a brand new input it's never seen before and predict what the output should be.
So here's the game plan for our journey. We'll kick things off with the big idea. Then we'll dive into the classic straight-line model, before completely shifting gears to predicting simple yes or no answers. After that, we'll see what happens when data gets messy and complex, and we'll wrap up by looking at how to build smarter, much more reliable models.
Okay, let's jump right into that big idea. Let's get a real feel for what regression actually does, and, where you've probably already seen it in action without even realizing it.
Let's just take that smartphone example. The inputs, right? They'd be all the tech specs, screen size, battery life, camera quality, you name it. The output is the final price tag. So regression learns from the history of tons of other phones how those specs relate to price. That way, when a new phone is announced, it can predict a pretty realistic price. And hey, the exact same logic applies to forecasting stock values or figuring out how many new subscribers an ads campaign might pull in.
To build these amazing predictive models, we have to start somewhere. And that starting point, the absolute foundation, is the most fundamental type, linear regression.
I want you to picture a scatter plot of data. Maybe it's house size on one axis and the sale price on the other. Linear regression, a method that actually goes all the way back to mathematicians Legendre and Gauss in the early 1800s, has one simple job. Draw the one single straight line that best slices through that cloud of data. That line, that becomes our predictive model.
But wait a minute. How do we define best? How does the machine know which line is the absolute perfect fit? Well, it uses a method called ordinary least squares, or OLS. Just think of it this way. For every single data point, it measures how far away it is from our line. That distance, that's an error. OLS then squares all those little errors and adds them all up. The best line is simply the one that makes that total sum of errors as tiny as possible.
So once we have our line, we need to grade it, right? See how well it did. That's where the R-squared value comes in. You can basically think of it as a report card for our model, with a score from 0 to 1. An R-squared of, say, 0.8 means that 80% of the changes in our output, like those house prices, can be explained by our inputs, like the house size. And it's simple. The closer that score gets to 1, the better our model is at explaining the data.
Okay, but what if we're not trying to predict a number, like a price? What if the answer we need is a simple yes or no? Or maybe we need to classify something into one category or another. For that kind of problem, a straight line just won't cut it. We're going to need a totally different kind of tool.
The key difference here really is the kind of answer you're looking for. Linear regression predicts a continuous value, a number, like a $799 price tag. Logistic regression, on the other hand, is all about classification. Its whole goal is to predict which category something belongs to, and it gives us a final probability, like, say, an 85% chance of being a yes.
So instead of fitting a line through the data points, logistic regression draws a line between them. It's creating a boundary, a dividing line that separates the positives from the negatives. Then, any new data point is classified based on which side of that line it falls on. It's that simple.
But it's not just about which side of the line a point lands on. Logistic regression also tells us how certain it is. It's basically a three-step process. First, it calculates the point's distance from that boundary line. Second, it converts that distance into what's called an odds ratio, which is just the odds of one outcome versus the other. And finally, it uses this really cool S-shaped curve called the logistic function to neatly turn those odds into a clear, easy-to-understand probability between 0 and 1. Okay, so we've got straight lines for predicting numbers and straight boundaries for classifying things. But let's be real, the world is not always so simple and neat.
What happens when the relationships in our data get way more complex?
Yeah, sometimes the true pattern between our inputs and outputs is a curve, not a straight line. For cases like these, we can use something called polynomial regression. Instead of a simple line, it uses a more complex equation, one with things like squared or cubed terms. This basically gives our model permission to bend and curve, giving it the flexibility it needs to capture those more intricate real-world patterns.
Now, all this flexibility sounds fantastic, right? But it actually comes with a hidden danger. Is it really possible for a model to do too good a job of fitting the data it was trained on?
Oh yeah, absolutely. And it's a huge problem called overfitting. This is so important to understand. An overfit model is like a tailor who makes a suit that fits a mannequin perfectly, down to every last tiny scratch and dent on its surface. But because it's so specific, that suit won't fit any actual person. The model looks incredible on past data, but it completely fails on new data because it learned the noise, not the real pattern underneath.
So, if overfitting is such a massive risk, how do we build models that are both powerful and reliable? Well, that brings us to our final set of techniques, which are designed specifically to create smarter, more robust models that don't fall into that trap.
Imagine you're a chef with hundreds of potential ingredients for a new recipe. How do you figure out which ones actually make the dish taste better? Stepwise regression is like a chef who methodically tries adding or removing one ingredient at a time and only keeps the ones that make the biggest positive impact. It's a brilliant, automated way to find the leanest, most effective set of predictors for our model.
Another really powerful technique to fight overfitting is called regularization, and it comes in two main flavors, Ridge and Lasso. They both work by adding a penalty to the model for making any single input too important. Ridge regression sort of shrinks the influence of less important variables, pushing them closer to zero. But lasso regression, it's much stricter. It can shrink the influence of unimportant variables all the way down to zero, which means it completely removes them from the model. It's pretty amazing.
Okay, let's wrap this all up. The main thing to remember is that regression is all about using past data to get a glimpse into the future. We saw how linear regression fits a straight line to predict a number, while logistic regression draws a boundary to predict a category. And finally, we explored how more advanced tools like polynomial, stepwise, and regularization help us tackle real-world complexity and, crucially, avoid that dangerous trap of overfitting.
And that leaves us with one final, really important thought. Every single model we've talked about is designed to make its errors as small as possible, but no model can ever eliminate error completely. They give us an estimate, a prediction based on probability. So the real-world question we're all left with is this. Knowing a model will never be perfect, how do we decide when its prediction is good enough to actually trust and act on? That's the challenge to think about. Thanks so much for joining me.